Math Review Part 6, Matrix Inverse. And this time, really, I'm using the word review pretty loosely because I'm going to show you some tricks that definitely were not covered in 380. So this is going to be more useful, I think, than some of the other stuff. So matrix inverse, what does that mean? Review the matrix inverse is the matrix that, when multiplied by the original matrix, gives you back the identity matrix. Now, when you learned about matrices in math class, they probably taught you Gauss-Jordan elimination. And here's a YouTube video. You can check that out if you want. You want to review how that worked. And those of you who still remember your math class and remember your linear algebra will think, no problem, I got this down. And that's great. Only we're not going to use it. I'm telling you, we're not going to use it in this class. And I don't think you're ever going to see this in a game engine. Maybe? I've never seen one. Instead, I see the analytical solution, which here's one. Here's a link to a page. And you will need this one for the lab. You'll need this one into the game engine. Just go in there and get the 4x4 inverse. And I've forgotten whether we have to do the 3x3 inverse for this class. But it's just a formula. You end up typing it in. It's a lot of multiplies and stuff, but it's just a whole lot of typing. It's monkey work, no big deal. Type that in, and then it becomes a function, and you can just call it anytime you want. But again, I'm not going to make you do this on an exam. I'm not going to make you do this on an exam. If you want to use Gauss-Jordan elimination on the exams, it'll work as long as you don't mess it up. But instead, I will ask you to do inverses using shortcuts. Now, what do I mean by shortcuts? It turns out it's super easy to invert the matrices we use in games. In math class, we talked about, in linear algebra, we talked about arbitrary matrices. They could be anything. And because they could be anything, you had to use these techniques to invert it. But because our matrices in the game engine tend to be these TSR things, we can do quick inverses. Okay, what do I mean? I mean a T matrix, a translation matrix. We just put the translation across the bottom of the matrix, right? That was how we made the translation matrix. How do you invert a translation? Remember, invert means undo. So if you translate by 10, 20, 30, how do you undo that translation? You just go back by 10, back by 20, back by 30, or you translate by -10, -20, -30. So to invert a T matrix, you just put minus signs on the T's. Boom. No Gauss-Jordan elimination needed. You just put 3 minus signs, wash your hands, and move on. How do you invert a rotation matrix? So say I have a pure rotation matrix. I want the invert. Turns out, all you got to do is transpose it. Now, I mentioned this before. I didn't really say what it is. Transpose means you just swap the rows for columns, right? Or thinking of it another way, the diagonal stays the same, and you just swap around the diagonal. You just sort of mirror it around the diagonal. So what used to be here, this used to go R01, R10, I misspoke. This used to go R00, 10, 20. But instead, we took the term that was here and put it here, took the term that was here and we put it here. Same thing here, we swap here and here, swap here and here. So again, just something you can do totally in your head. You just transpose it, bang, zoom. You don't need any elimination or anything. Okay, the last one we did was a scale matrix. So if you have a scale, like I said, in the previous one we had a 10, 10, 10. You multiply by 10. How do you undo that? How do you undo scaling up by 10? Well, you scale down by 10, or you divide by 10, right? You take 1/10. Okay, so there you go. You just take whatever was in the x term of the scale and you divide it. Whatever was in the y term of the scale, you divide it. Whatever was in the z term, and you divide it. And it could not be any easier. Super easy, much easier than elimination. You say, what if you have this combined matrix? It gets a little trickier here. If you have the SRT combined and you want to invert that whole thing, there's still a trick to it. And it turns out to not be all that difficult. You could still pretty much do it in your head, just about do it in your head. Okay, and here's how. First off, remember that if you invert a quantity, you can invert the individual components and reverse them. So I'm doing that here. I'm going to take the t, separate the inverted t out, and put it in the front, taking it from the back to the front because it's coming out of the parentheses. All right, and the t inverse was unbelievably easy to get. Even in the SRT matrix, the t was just written right across the bottom. So all I do is just take whatever's written across the bottom and I put minus signs. And there's my t inverse. So that leaves us with this SR inverse to try to work out. So let's look at what is SR. SR looks like this. I just take the S and I take the R. And notice I'm giving you different values for X, Y, and Z. I said I could do that. So I take the S and the R and I multiply them and I get this. That's just what it looks like when combined. Before I go on, I do want to point out, check this out. I have the rotation part going across, but I have SX goes across, SY goes across, SZ goes across. The scale is just multiplying across the rows. That's going to come up. Important. Okay, so if this is my SR, let's get the SR inverse. And again, I'm going to use this same property that if I break the parentheses, I can invert the individual terms and reverse the order. Now, the R inverse we learned was just R transpose. That was pretty easy. And the S inverse we learned was just you put 1 over. And so that's going to be pretty easy. Let's take a look. Here we are. So I've transposed my R's, and I've inverted my S's, and I do reverse the order, right? And so I'm out of space. Okay, I just rewrote this. I've transposed my R's, I've inverted my S's, and I put them in that order. So let's multiply that out, and that's where you get. Now the scales are going down the columns instead of across the rows, right? That's kind of going to come up again. Why am I looking at this? This is what I'm trying to achieve. This is the inverse of SR. So if I can get this, I've got it, because I already have my T inverse. That was super easy. So if I get this, then I can get it. So one way to do that is to get what the scale is and get what the rotation is. Getting the rotation is actually the tricky part. Getting the scale is very, very easy. How did I get the scale? Remember that I said the scale was multiplied across the rows, right? So the X scale is just the magnitude of this row of the matrix. The Y scale is just the magnitude of this row of the matrix, and the Z scale is the magnitude of this matrix, right? So I just get the magnitude, get the magnitude, get the magnitude. That gives me the scales. I've got this part of the matrix. Now I just have to get this part. One way I can get that is if I just divide what was given by the magnitude, then I'll get this out. And then I'll be able to have R00, 0, right? I'll take this term from the original matrix, divide by the SX that I've got, and now I have R00, 0, and then I divide by SX again, and I have R00 divided by SX, right? But it turns out there's even a trickety trick on that. What I was given, keep in mind what I was given was SR. There was also a T down here, but it's just super easy to just strip the T off. So I was given SR as my original matrix. If I just simply transpose that, I get this. This is SR transpose. and I'm trying to get this. So let's compare these two and see how they're different. This one has Sx times R00. This one is R00 divided by Sx. And see that pattern just continues. It's always, instead of multiply, it's divide. How do we go from one to the other? Well, let's take this matrix here, and we'll take each of the first column here, and I will take it and I will multiply the numerator and the denominator by an Sx to get Sx in the numerator, Sx squared in the denominator. What's up with that? Why would I want to do that? It's a little bit confusing, but remember, what I was given was this. This was the original matrix I started with. What I'm trying to get is this. What I've just done is numerically identical to this, right? I just multiply the numerator and denominator times the same thing. That means do nothing. So this is legal. It's just kind of, it looks ugly, but this is the same as the inverse I'm trying to get. But now compare this and this, and you'll see this divided by Sx squared gives me the inverse that I'm looking for, right? So what is up with that? What's up with that is I take the matrix I'm given. I take the magnitude of this, since I transpose it, take the magnitude of this column. It would have been the row in the original, right? Take the magnitude, that gives me Sx. But how do you get a magnitude? You take the square root of the sum of squares, right? So you take this term, you square it, take this term, you square it, take this term, you square it, you add those up, and that gives you the square of the magnitude, and then you'd square root it to get actually what Sx is. But hey, look at this. We need the square of the magnitude now. So you just get the square of the magnitude and divide that column by the square of the magnitude. Bam, there's your inverted matrix. So let's now get back to the combining the t that we had with the SR that we just calculated, and we'll combine those like so. Now, watch out for this. A lot of people make this mistake of thinking, oh yeah, I remember how to do that. I just put the translation across the bottom row. Well, that was true when we did SRT. We did SRT, the t just goes across the bottom row. This is t times SR quantity, right? And that means the t is in the front, and we have to actually multiply that out. The rest of the t matrix is still the identity, so you don't have to bother multiplying that. You just repeat. These terms are all going to be correct. But for the bottom row, you have to take this vector and multiply it through these terms to get the answers. So actually do that multiply. So let's do an example. What we just went through is how you would program this in a general format. Like if you didn't know what the numbers were going to be, you have to write a code to do it. And we'll need to do that in the lab. But if I do an example on an exam or in an assignment, it'll look like this, where I'll give you actual numbers to work with and expect you to work it out on paper. To do that, we're going to need to break our matrix into the SRT components. And we'll be inverting that by inverting them individually. And remember, when you invert them individually, you reverse the order. So that's what we'll do. So we'll need to be able to get the t from this matrix, and that's very easy. It's just for the bottom row. So here's the t, 10, 20, 30. To invert those, we just put minus signs. So that's super easy. No one's going to have trouble with that. Just put minus sign, minus sign, minus sign. There's your t inverse. That one's done. Next comes the r and the s. We really have to get the s next. So to get the s, we need the magnitude of the three rows here. So the magnitude of this top row, we can tell. In this case, these numbers are super easy. I look at it, there it is. It's magnitude of 1. This magnitude, the magnitude of this row, is 2. And the magnitude of the third row, the z row, it's the 0, is 3. So my scale will be 1, 2, 3. Once I've removed the scale from this matrix, I would have a -1 here, a 1 here, and a 1 here after I've removed that scale. That'll be my rotational part. So remember, to invert the rotational part, we transpose that, and so that is here. I have taken the -1 that was here and transposed it down to here. It appears right there. I've taken the 2, which when remove the scale, that's going to become a 1, right? So take that and transpose it up to here. That's right there. And then this is my 3, my z term, which when I remove the scale will be a 1, and it's on the diagonal. So even after transposing it, it lands right there. So for the bottom row, I just fill in zeros and a 1. And that's my rotational part inverse. So the last term here is the scale inverse. And remember, that one was also quite easy. We just took the scale of the x-axis and do 1 over. Well, the scale of the x-axis is 1, so 1 over 1. The scale of the y-axis was 2, so 1 over 2. And the scale of the z-axis is 3, so 1/3. And so here's my inverted scale matrix. All right, all I have to do now is combine them in this order. First, I'm going to combine the R and the S. You can do them in any order, but this turns out to be easier. So combining the R and the S, remembering now, this one actually tripped me up. I had to re-record this section because I went too fast and I made this mistake and I combined them in the reverse order. But they are RS now because I'm inverting. It starts out SRT. When I invert, it's TRS. So RS, when I multiply them, I'm going to go across this row, down this column, across this row, down this column, across this row, down this column, right? So across this row, down this column, ends up with a -1 right there. And across this row, down this column, I've got the 1/2. Across this row, down this column, produces that 1/3. The other thing you can do is remember that the scale just goes across now. Instead of, when we started up here, the SX scale went this way, SY scale went this way, SZ scale went this way. But we've reversed it, right? This is the inverse. So now the scale, SX scale goes this way, SY scale goes this way, SC scale goes this way. So, if you remember that, great, or just multiply them out. The numbers should, if I'm asking you to do it on paper, the numbers should be easy enough to do stuff like this. So here's my R transpose S inverse. Let's just stick the T inverse on the front of it, like so. And you've got it. We just got to multiply this out. You may be tempted to say, oh, I just write -10, -20, -30 here. But that was true when it was an SRT, but now it's a TRS. So you actually have to multiply this part out. You can't just write it in. This part here, this is the identity matrix part of the T. That's not going to do anything up here. So this whole section, this 3x3 section, you can just repeat it. Just write that. You don't have to do that one. But this last row, you do have to multiply it out. So if you see, we're going to get -10 times 0 plus -20 times -1 plus -30 times 0, 1 times 0. So we had a -20 times -1. So that's 20 is going to go in this first thing. See that? So we multiply it all out. Here we go. I've got it rewritten here. So here's the original matrix. Here's my T inverse, my RS inverse, and I multiply them out, and I should get this. So I just duplicated this 3x3, and then I write across the bottom, or I have to multiply out across the bottom. See, I can't just write the numbers. I have to actually multiply that out. Once again, the -10 as times a 0, -20 times -1, so I got 20 here. And on this one, it's the minus 10 times the 1/2 that comes out and gives me a minus 5. And then in this last column, I get a minus 30 times 1/3. So I get the minus 10. So there you go. That is how to do that. And as you can see, most of it is just writing straight off the top of your head. But you do have to be careful with the multiplies when you recombine those matrices. And I think you'll agree this is a lot easier than trying to do Gauss-Jordan elimination. If you want to do Gauss-Jordan elimination, I will accept that. But it's more steps, a lot more writing, and a lot more opportunities to make a mistake. So I prefer this way. And the main reason I prefer this is because I really want to stress that you can look at a matrix and tell me what that matrix means just by looking. You can look at this matrix and say the position of this object is 10, 20, 30. So if I want to look, where in the world is this object? Well, just go to 10, 20, 30 in the world. You should find your object waiting for you there. And, oh, how big is this object? Well, this object has been scaled in the y-axis and scaled in the z-axis. I can look at this matrix and tell just by looking what it is I'm talking about.